Hi, welcome to QuBites, your bite-sized pieces of quantum computing. In this first episode, we're going to talk about the basics of quantum computing and making sure we're all on the same page, right? So we'll talk a little bit about quantum mechanics, but don't worry, you don't need to have a PhD in math or physics to follow along. We're really focusing on applied quantum computing and the impact we're already seeing today with quantum computing and especially quantum-inspired computing. My name is Rene Schulte. I'm Director of Global Innovation at Valorem Reply, where I lead research and innovation and pretty much focus on emerging technologies. And of course, quantum computing is very much emerging technology. I'm also a Microsoft Regional Director and MVP, which are community awards provided by Microsoft, the independent experts that share the knowledge. So I do a lot of conference speaking, open source projects, blogging, and very active on social media. So what does quantum computing actually mean? Well, I think it's fair to say that it's one of the most disruptive technologies we will see, or we're actually seeing right now in the 21st century. The hardware stack, it's still a bit in its infancy, but again, already amazing progress is being done, and I'm sure we will see amazing things in the next couple of years there. We're going to mainly focus on the software stack, because this is where we're seeing huge impact already today. And quantum computing in general allows us to solve problems that have been unsolvable before or have been unsolvable in nonlinear time, right? And so quantum computing provides us the opportunity to solve challenges that are just too complex with classical computers, right? And so all the big vendors are working on quantum computing technology stacks, partly hardware as well as software, right? And if we're looking at Microsoft with the Azure Quantum offering, they're of course also having partners like IonQ, Honeywell, and so on, as that you can use as part of Azure Quantum, right? But also Microsoft is working on their own research, especially with topological qubits, which might be the winning technology in the future. But again, very much in a research phase, but you can already apply for the early access for Azure Quantum. And if you have a need, you might be able to also leverage some of the hardware vendors Microsoft is working with. But also Microsoft being Microsoft and having a strong developer community and focus on the developer stack, they have amazing offerings here with the QDK, the Quantum Development Kit, as well as this new programming language called Q#, right? So what is actually quantum computing based on? Well, it's based on laws of physics and quantum mechanics, which is laws of physics that were developed around 100 years ago as theories, right? But since then, all these theories has been proven in experiments that these are actually true, right? And some of these things might be a little bit spooky and sound weird, but it has been proven in experiments that this is really how our universe, how the world around us operates at the smallest scale, right? So we're talking about molecules, atoms, and a subatomic particle size like photons, electrons, and so on, right? And if you go to the small dimension, certain behavior can be observed that is happening. For example, entanglement and superposition. And if we're looking at classical computers, they're dealing with bits, right? They can be off or on, 0 or 1, right? With quantum computers, our basic unit of information is a qubit. And a qubit can be in superposition, which means it cannot just be 0 or 1, but it can be 0 or 1 at the same time. Sounds crazy, but that's the case. And so if you look on the visualization here with the sphere of the qubit, basically a qubit can be all the values on the sphere, right? Not just the north and the south pole with 0 or 1, but all the values and in superposition. And the awesome part is you can even compute while a qubit is in superposition. You can apply certain operations and gates to these qubits and basically run these operations in parallel, right? Because you can represent multiple values at the same time, basically. And you can store a lot of stuff and you can compute a lot of stuff in parallel. And that's why we can solve these crazy problems in almost linear time for certain problems and make them actually solvable, right? And this other thing is called entanglement, which you can see on the slide here. That's actually the first photographic proof of entanglement. And so basically what it means is you can, take these particles or qubits in the case, entangle them together, and then they will stay connected. Even if you split them apart, like, send them in different directions, they will still somehow be connected. And if you apply a change to one of these that you separated, they're still entangled, and you can observe the same change on the one that was actually separated, because they will be entangled initially. And you can take advantage of that with qubit, entangle them, and so can do a lot of computations at the same time. It's a crazy concept, but it works, and it was proven. Again, this is the first photographic proof actually of entanglement in 2019. By the way, Albert Einstein called especially entanglement a spooky action at a distance, right? So he was very skeptical, but again, since then, all of that has been proven, and we can use it for computation, and that allows us to solve complex issues, right? So some of the key areas of quantum computing, and the ones we're going to focus in the series, are quantum machine learning, basically using machine learning on quantum computers, right? These are like these huge complex problems, and of course they're well suited for quantum computing. Then quantum security, also super interesting topic, right? Because we can take advantage of the characteristics of quantum mechanics. For example, if you have your particle in a superposition state, if you want to measure it, if you want to get the value, it has to be collapsed, right? So it will fall down to a 0 or 1 state, basically. And you can take advantage of that with quantum security. For example, imagine a key exchange, right? You need to send a secure key from A to B. And if there's someone eavesdropping in the middle, you will know it at the end, because the state will collapse. So you cannot clone it, and eavesdropping is basically not possible. Also, of course, quantum cryptography is a very interesting part, because we have to imagine in a few years, when we have quantum computers with a lot of qubits, all the current cryptography algorithms like RSL will be obsolete. They will all be crackable in a short amount of time. And therefore, post-quantum cryptography is a very relevant research topic. Mainly, we're going to talk about quantum optimization in the next few episodes. And quantum optimization is especially relevant when we're talking about quantum-inspired computing and quantum-inspired optimization. What that means is basically you can take advantage of quantum mechanical behavior, but don't run it on a quantum computer, but run these quantum-inspired algorithms on classical hardware, like high-performance computing or GPUs and so on. And you can already see that algorithms, quantum-inspired optimization algorithms, are outpacing classical algorithms on classical hardware, right? So you can run quantum-inspired algorithms on classical hardware. They're even faster than your state-of-the-art optimization algorithms, right? And why is that the case? Well, if we look at quantum-inspired optimization, let's actually think about what is the challenge? What are we looking at, right? And in general, you have a so-called objective function, which is typically a cost-saving function, right? You want to reduce the cost of your parameters, or you want to reduce the energy, or increase fitness, whatever, right? And if you look at the slide here, you can see there's the energy, right? And we want to find, of course, the least amount of energy we have to spend for our, to solve the problem, basically. And so we want to find the global minima, which is always a challenge, and especially with classical algorithms, you sometimes get stuck in the local minima, right? The non-optimal way. And with quantum-inspired optimization, we can take advantage of behaviors that can be observed in quantum mechanics, like quantum annealing and the quantum tunneling effect, right? So instead of having to go up and, getting to a new energy niveau to get over the hill, if you will, to find the global minima, you can tunnel through it, right? And that's, of course, pretty amazing, actually. And that, of course, can only be observed with quantum computers. But we can also simulate those with thermal annealing and other things, and basically run these quantum-inspired optimization algorithms also in classical hardware. And again, that is already providing a huge value. And we're looking at use cases for smart cities, 5G mobile networks, financial optimization, or think about public transport scheduling, right? You need to optimize how many people can be, transported, and how many trains you can run and so on. Or workforce management, right? Assigning working tasks to people, or you have a fleet of vehicles out there in the field, right? You want to optimize how this is spent, reduce the cost there. Or think about how you load a ship, a plane or truck, right? Optimize the loading of these kind of pieces. Financial optimization, like portfolio optimization. And of course, very much quantum chemical challenges, like folding molecules and, creating new pharmaceuticals, fertilizers, and other chemical processes, right? And so that's what we're going to focus on in the next few episodes, actually. And so thanks for your attention today with QuBites. I hope you find the session interesting, and stay on us with us. The next few episodes will be about quantum-inspired computing and showing you real projects where we're seeing impact already today. Thank you, and feel free to reach out. Take care, my friends, and stay safe.